In this problem, we're told that we're trying to find an equation of the form f of x equals ab to the x. So this means that we're supposed to find an exponential function for each of the three cases. We have three different equations. The information is just given, one in tabular form, one as a set of data, and one as a graph. So remember, if something's in the form y equals ab to the x, the a and the b represent two different things. The a is always the vertical intercept, or the initial value. It's what you get out when you plug in 0. Well, with the data, and the first one, it's obvious what you get when you plug in 0, because the data tells me if you plug in 0, you get out 50. So the initial value is going to be 50. I'll do that first because it's so easy. The base is a little bit more difficult to figure out. The base in an exponential function is called the growth or decay factor, or sometimes I like to call it the multiplier, because by definition, it's the multiplier that you use to get from one output to the next as long as your x is increasing by 1. So again, b is the multiplier that you multiply one y value to get to the next y value every time x goes up by 1 unit. It's convenient in each of these examples that x is conveniently going up by 1 unit at a time. So to quickly remind you how to find b, here's just a little thing I wrote up really quick. The idea is that to get from 50 to 45, we need to multiply by b, the multiplier. So if you wrote that down as an equation, you have 50. You're multiplying by some number b that we're trying to find. And when you take 50 and multiply by that number b, you get 45. So if you set this up as an equation and solve for b, you would do so by dividing both sides by 50. And what you'd get is these would cancel, and b would be 45 divided by 50. So this is just to teach you that to find the b value, what you can do is you could find a bunch of ratios where you simply just take the later y value and divide by the former. So I'm going to do that right now on this graphing calculator. I'm going to take 45, I'm going to divide by 50, and it tells me that the multiplier is 0.9, meaning if you took 50 and you multiply by 0.9, you'd get to 45. The idea is if you keep multiplying by 0.9, you should get from one y value to the next. If you want to verify that it's true for the rest of them, you'd have to do a lot of button pushing. So this time I would take 40.5, the later y value, divide by the former, which is 45, and I see that still we get a multiplier of 0.9. Now it may not come out exact, but I don't think Math.AS is being that picky. 36.45 divided by 40.5 is going to be 0.9. The last one, 32.81 divided by 36.45 gives you almost 0.9. Again, I think we're not trying to be too picky. Technically, this isn't exactly exponential, but we're going to go with it. I'm going to say that the base is 0.9. Sometimes I let my students do a little shortcut to this, but your teacher might not like this. Let me clear this out. If you're trying to find an exponential pattern, when we did the 45 divided by 50 and got that it was 0.9, it would just be a few button presses less that if you just said, let's just try it. Let's just try 50 and successively multiply by 0.9 over and over again and see if that's indeed the correct multiplier. So I'm going to take 50, multiply by 0.9, get 45, multiply by 0.9 again, and get 40.5. This is where it gets easier. Once you do the same operation twice in a graphing calculator, if you just press enter, it assumes you want to keep doing that. So when I press enter, it'll multiply by 0.9 again, giving me the 36.45. Pressing enter again, it gives me roughly the 32.81. So let's finish this problem out here by writing the equation. The equation is going to be the form ab to the x. We've already figured out that a is 50. B we typically put in parentheses. So I'm going to put it in parentheses. Our b value, our multiplier was 0.9. And I need to raise that to the x power. That would be the first equation. If you want to make sure you type it in right, I suggest you hit preview. It says that the syntax is okay. I'm going to go down. Next one is basically the same process, except instead of giving it in tabular form, we're giving it as a set of data. So I'm going to clear my calculator, repeat the process, but notice this is important that my x's are going up by 1. 0, 1, 2, 3. Remember, b is the multiplier every time x goes up by 1 unit. So you'd have to be careful if these weren't going up by 1s. So I'm just going to repeat the process, take my later y value, 23, divide by 20, see what I get. I get 1.15. You can either now do 20 times 1.15 over and over again to see if you generate this list, or most teachers actually like you to keep finding ratios just to reinforce how to do the problem using ratios. So I'm going to do it this way. 26.45 divided by 23. If it's purely exponential, we should be getting the same base every time. So far, so good, 1.15. The last calculation would be 30.42 divided by 26.45. I don't think this is going to come out perfect. I think we need one more decimal place on that last number. But like I said, it's roughly 1.15, so we're going to use 1.15 as the base. So I'm going to type that in. The initial value is pretty easy. The initial value A is always what you get out as an output when the input is 0. The data tells me that. When you plug in 0, you get out 20. So that's simply the number 20. Oops, not 20. And then my equation g of x would be the form a b to the x. So a, my initial value is 20. In parentheses, my b was 1.15. And then I need to raise that to the x power. Again, if you want to preview it to see that your syntax is okay. Sometimes what happens is they use the input variable t and students use x instead. It'll give you a syntax error to remind you you're not using the correct variable. So on this one, we have a graph. It's basically the same thing as before, except now we have a graph. So I would probably have to label a few points, but as I said before, b, when I find my b, it's what you multiply the y values by to get from one to the other every time x goes up by 1. So because I don't have a table for me where the numbers are chosen for me, I need to do the choosing, but I'm going to do it so that x goes up by 1. So I'm going to start by looking at my initial value. If you look at the vertical intercept here, since each one of these tick marks is 1 unit, the y-intercept right here, the vertical intercept would be 0, 1. So it looks like my initial value is 1. Now to find the base, it's going to be a little bit trickier. I'm going to have to keep increasing x by 1 and see what happens to my y values. So to do this, what I did is before making the video, I just made out this quick little chart here just to help me. So we've already looked at the point 0, 1. So here's my x values, here's my y values. And before I made the video, I just counted off. If you move over 1 unit to x equals 1, y goes up to 1, 2, 3. So I just, to keep things organized, made a chart here. If x is 1, y would be 3. Moving over 1 more unit in the x direction again, you know, from 1 to 2. So again, it's critical that if you're finding b, that you make sure x goes up by 1. So we were at 1, 3. If I let x go up by 1 again, you'd be up at 4, 5, 6, 7, 8, 9. So that gives you the point 2, 9. So you could form ratios here, 3 divided by 1, 9 divided by 3, but because the pattern's so clear, I think it's pretty obvious that to get from one y value to the next, you simply multiply by 3, and then multiply by 3. Therefore, every time x goes up by 1, your y value is triple. So my base is 3. So let's write that out as an equation. So my base is 3. My initial value is 1. You don't need to write it, but I'll write it just so that you see that I'm doing something. So the original equation is going to be the form a b to the x. A is 1. Multiplying by 1 does not need to be written, but I'm going to do it so you don't think I've forgotten it. In parentheses, I'm going to put my base, which is 3. And then don't forget that you're raising to the x power. That's basically how you do the problem.